So when you search for the fall semester, and you put in my last name. I gotta tell you, the first time I saw this, I was shocked to find out I was teaching a management course. Then I looked at what my name is not Stephen. And then I went, who the hell is Stephen? That is not the man I'm married to. I gotta find out who this guy is, because the last name Whiting actually is not that common. Anyway, so when we're looking at who's teaching what course in the fall, it very well may be a damn lie, okay? So let me tell you what happens for the fall semester. So Dr. Orji has to get the fall semester put together so you guys can register, right? Because not everybody takes some courses. And so what they do is they just take the fall schedule from last year and move it forward. So that's how some of you get lulled into taking classes with a specific professor, and then you get there and you're like, oh shit, what happened, right? Like, so that happened in CS1 last fall. Everybody thought they were taking it with a group. And then they get there and it wasn't a group. And they're like, Whiskey Tango Foxtrot. I just got totally snowed. Okay, so that's why the schedule looks the way it is. So chances are, I am not teaching OO in the fall. I'm just telling you that. It will probably be Dr. Polinos, okay? So it probably will not be me. Because if I keep CS1, there's probably, the odds are against me teaching OO. So that's the secret to how the fall semester gets put together. Yes? I am doing the summer. I'm definitely doing the summer. In the summer, I'm doing CS1, OO, and my HDI one. I'm sorry? That one is definitely me. As far as CAP 4104, no one else is ever going to teach that class until I die. Okay? So, or I get fired. There's a chance, given, my discussion on drugs and my insanity, there is that opportunity that I may get fired at some point. But, I'm sorry?
It's all right.
Screw that. Fuck it, I function in the real world, and I gotta tell you, we are not polite. So, because I gotta tell you, when I saw I was teaching internet applications again, I'm like, I hate that class. Because it's at 7:30 at night. Who wants to go to class at 7:30 at night? By then I've had dinner, I've had a couple glasses of wine. I shouldn't even be driving, Anyway, I just want to tell you that for those of you that are looking forward to the fall semester, don't believe everything you see about who's actually teaching it. Okay, we're just placeholders. In the summer, they just put the word staff. So you're like, who's professor staff? That would be all of us. Yes, sir. Say that again? It's a 12-week one. It is May 17th to August 16th. So, questions?
Oh, no.
No, yes, that class really is 7:30 to 8:45. It's tough to ask. It does.
That's what the only system software like.
Yeah. Not excited about it. But I'll do whatever I have to because I am a team player. That's what I do. Okay, we need to finish talking about Big O. So the other damn lie I told you on Wednesday was I would have an assignment 3 for you this week, for today, and I don't. And let me explain to you why. Because I need to change what our assignment 3 is going to be. Okay, so one of the things that they've done with the foundation exam, one of the things that they've done with the foundation exam is, so with the discrete foundation exam, it was very, very specific what you could expect from each section, okay? So there's like, and this section, section part A, section 1, it would be this. Definitely across the board, this is what you need to study. So until last fall, the CS portion was not that organized, but they got it that organized this last fall. So we got our shit together. How awesome is that? Okay. So here, what this is telling you is very explicitly what you can expect. So here, with the recursion, so if you have a terminating condition, what is that called? Base case, right? So we talked about base cases. We talked about an algorithm for a non-terminating case. What do you end up with? Infinite loop, right? Okay, so we're reducing our overall problem into smaller instances. Okay, so here, like towers of Hanoi is one of the things that's really common. I kept telling you, it's really common. You got to understand this crap. Permutation. Words are hard. I did not give you permutations, and Jonathan told me we needed to do that, and I totally friggin' brain dumped it. So your next assignment is going to be recursion with permutations, because you have to know it, okay? So I got to put that together for you. And then the flood fill thing. So we have to do this because I want to make sure that you're prepared. These are topics that we need to cover. So then the second section here is specifically going to be summations and algorithm analysis. So that's what we're doing now. We're talking about algorithm analysis. First we're talking about big O, then we'll do summations, and then we'll do recurrence, okay? And so, we need to talk about all of that. And then section 3, this is what we're going to get into. We're going to do our abstract data structures. So we talked about stacks and queues already, right? So we're totally good here, where we have we talked about our array implementation of a stack and a queue, and we talked about our linked list implementation of stacks and queues. Those code examples I put out there. So initially, I just did the linked list part of it, but Jonathan says, no, show them the array part of it. And so we have that. We have the array and the linked list version of it. So we're totally good here. So what we need to get into later this semester, so once we get past our whole linked list concepts here, we need to do binary trees, we need to do the ABLs, we need to do the hash tables, binary heap. And we've already done base conversion. Okay, so that's where we are. That's what we're tracking on. So again, algorithm analysis, our data structures, best, average, worst cases. So that's the big O. I'm trying to figure that out now. Different implementations, need problem analysis. And then we have to do timing. And more linked lists. I gotta do equal to with linked lists, don't we? So this is really important that you understand how to do this from a linked list perspective. So those of you that didn't feel really confident with assignment 1 and assignment 2, I highly recommend that you go back and try it again if you didn't get a satisfactory grade on it. You need to make sure you understand how that works, okay? It's very important. And here, with assignment 2, when I told you you need to do the recursion part of our linked list, okay, so this is why, because it's here. It's one of the things that we need to test you on, all right? And then more binary trees and sorting. And then this discrete part, you don't want me involved with that. I don't know what the hell these words mean, okay? I could probably struggle. Anyway, so that's the deal. That's why we're doing what we're doing. So we're going to do big O, and then your assignment 3 is I'm going to do the permutations for you, because we have to do that. And then we have our other options there with our algorithm analysis that we continue with in our different sortings. We're going to do permutations. And so I'll get that out. I'll get that put together this weekend because you guys absolutely need to understand that. All right, so let's get through big O so that we can move on after this on Monday. Okay, so this is kind of where we left off on Wednesday. We left off with some code so that all the words and all the mathematical expressions that we were looking at actually meant something to us from a code perspective. So we have these two different functions. We have this first function where it stops if the first function stops running when k is no longer less than or equal to n divided by 2. Whereas the second function, and for j stops running after j is no longer less than or equal to the value of n squared. And so how do we determine which has the most significant impact? That's the purpose of big O, the most significant impact as the processes are functioning. And so here, when we're looking at our first loop, it runs n divided by 2. The second loop actually runs n squared. So how we figure that out is we just add those operations together, okay? So here we have our n squared plus our n divided by 2. But from a big O perspective, which one is more significant? That n squared, right? Because the n squared is significantly bigger than n divided by 2, because n squared is going to grow exponentially, while n squared just kind of gets smaller and smaller. I mean, n divided by 2 just gets smaller and smaller. That's awesome. Okay, so these are just some common big O that are out there. So here's some common orders, and this is really from the slowest to the fastest as far as how long it takes to run. So one is just a constant. We talked about on Wednesday, this constants really have no significant impact for the most part. It doesn't even matter how big that constant is. It could be a million. Still doesn't matter. Constant is a constant. It's never going to change. Okay, so here our one is a constant, never going to change. So the next one is log n. Log n is slightly faster than a constant. And then n is just linear, okay? Because the n just increases by 1. Well, it increases by some value all the time, or decreases, but it's linear, right? So then our polylog is n terms of log n. And then we have our quadratic with our n squared. And then our cubic with our n cubed. Then we come into an exponential where you have some base, and it's raised to a power of n. And then finally our factorial, which just is insane because you almost can't even calculate it sometimes. So we're going to look at that individually. So individually, if you look at this chart here, so the first one was 1. We had a constant of 1. So big O of 1, or order 1, is a constant time. Okay? So it doesn't mean it only takes one operation. It just means that the work doesn't change. Regardless of what n is, 1 is just a 1. It's not going to change at all. And so it's just constant. So that's why when we do our evaluation of big O, we drop our constant because that constant is no significant impact. So why would you use this? Well, maybe you just want to find the smallest element in an array. So in this case, there's nothing to search for because the smallest element in a sorted array is always the first value, right? Because it's sorted, lowest to highest, unless you sort the array the other way, and then it's the last guy. So the second one here, we're talking about log n. So log n, or order n here, is linear time. And so with this linear time of order n, it doesn't mean that it's only n number of operations to function. It could be, 3 times n and 7 times n if we have some constant that multiplies times it. But it just means that the work that it takes to actually perform those operations, it changes in proportion to n. All right, so let's say here the example is our input size doubles, so the running time doubles, right? So if n is 2, and then it's 4, and then it's 8, as it doubles, then the time it takes for that process to run doubles, okay? So what problems we deal with is kind of, O sub n, big O of n is usually what you're dealing with when you are examining your data. So now we have our n squared. So this n squared is considered quadratic. And so if the input size doubles, then that running time increases by that factor of 4. And then when you have your cubic, so our order n3 to the power of 3, so it's a factor of 8, right? Think about base 2, okay? So base 2 squared, that's a 4. Base 2 cubed is an 8. And then here, this polynomial, wow, words are hard today. Polynomial time. Okay, so this is where you start getting into problems because the high running time, sometimes, the processor just kind of goes, I can't deal So you kind of try to avoid this just because you could get in trouble with your processor. And then when we're dealing with our exponential, so this is some base value raised to the power of n. And this is, wow, so it's more of a theory than practical just because reasonably, I don't know, it doesn't really run that well because it's just the processing time required for this is just really insane. And then it's even worse when you get to your factorial. Oh my goodness, your exponential here, the input size is bigger than 10, it just blows it out of the water. There was an example that we did in class, somebody told me, oh, the college, okay, that college program I put out there. Somebody kept putting in values until they didn't get it to work anymore. And they said once you put in like 13 discs, it just kind of like crashed and burned. Who was that that told me that? What do you guys do? Maybe it was in the 1130 class. Oh yeah, okay. Yeah, so this is a really good example of n being too big, okay? So let me show you this really quick. Okay, so this example, we were actually allowed to put in what we wanted to for how many discs. So let's say we put in 8, and it still does a pretty good job, okay? It's kind of processed it pretty quick, right? Run it again. Okay. Let's try 10. Okay, so it's going, yeah, sure, I'm cool with that. Let's try 13. It's going. Okay. Maybe my computer is just better than yours. So this is 20. Woo, it's going, huh? Wouldn't that be fun if I asked you guys to write out the call stack on 20 discs? It would take you the rest of the semester to do that. Going. It's going. All right, so, I'm not going to crash and burn, but, it's taking a while here, right? I mean, think about the call stack on this, on 20 discs. Holy crap. There's 20 of them. Woo. We could be here all day. All right. No, because we have our base case, so we never be infinite. Let's see if that finishes it anytime soon. Okay, so this is an example, the input sizes that are really large. So that's an example of an input size that's really large from a recursive perspective. I mean, you think about all the recursive function calls that just got stacked down there with 20 disks. Holy crap. Think about with 20, there's 20 of them. And then the value of 19, there's 19 more on there. And then 18, there's 18 more. And, so it's like, it's an exponential. So it's 20 to the 20th power. Does that come right? Is it? 20. Yeah, 2 to the 20th minus 1. Pretty big number. I'm not even going to try to do math. I don't want to embarrass myself. So I used to be really good at math, and then I got into computers, and I'm like, wow, who needs that? I could just put it in the computer.
It's over 1 million calls.
Is it? It's running. My computer's badass, by the way, because it's processing that shit. All right, so here. So our big O. So we're dealing with the log n. We're dealing with logarithmic time. And so log n from n times log n is just a little bit bit slower than the linear end itself. But from sorted algorithms, it actually works better. And then when you're dealing with just straight up log and logarithm time, again here at the input time logarithm time is reduced only by a constant amount each time full. So any algorithm actually has the data, so that will end up with a log n algorithm. Yes. Oh. Did I say that? Come on. Ah, shit. Crash and burn. Huge fail right here. Damn it. That did wear my battery out. Oh, my computer's going, what did you do to me? And welcome to Microsoft world where you just gotta do a hard reboot. So we have about a 5-minute break here. Gotta love Windows. What do you want to talk about?
Solid state hard drive.
I know, wouldn't that be killer? I can't afford that. I would love solid state hard drive. Understand?
This class, are we learning how to, or is that more of the street learning how to drive? On which will let you know that.
What do you mean?
Like you have the code first. It's very easy.
Yeah.
But some situations you'll have to come up with a complicated equation and then decide